All right. Good morning, everyone. So for today, we're gonna study about the vision transformer. Okay. The the existing idea is like when you want to do the computer vision, mostly the model that you use is about the LesNet or CNNs. Yeah. So that that come up with this question like, can we use transformer to do a image classification task? But they still have a question like, when we do a transformer, we do about the sequence of the sentence. Can we change the image to be as a sequence or something like that or not? So this paper they try to propose the solution called the patch. Okay. So the idea is like, let's say you have image, you just make them as a sub image. Okay. But inside the technique is called a patch. Okay. And then you put this sequence of the image to the linear population of the flattened patch. Okay. And then add them with the positional embedding and put them into the transformer inside of the each layer. Okay, so we're gonna try to understand like how does this one work. Yeah, but because this is the classification, okay, so the idea is all the same as bird. So you just add one more token, okay, for the classification tokens and use this token, okay, to multi-head and try to classify a task that you want. But so for today, I just use only the simple data set, okay, which is MNIST. Yeah, this one is easy, like it just predict image with the number. But yeah, we check the step first. How does VIT work? Okay, so they just split, yeah, as I said earlier, and fatten and put to the linear embedding at the positional, feed to the token as a standard encoder. Try to pre-train them and fine-tune with some dataset tasks that you want. Okay, let's get started. How does patching work? Okay, so just run and test first. So I test with the test data set is yeah, we have 10 and test. Okay, but I split train data set 80% and give wow data set to 70%. So we have this link. So I can check first what does the tail loader give me. Okay, so you can see that yeah, image, they provide this image for me, but the information that they have inside is a bad side, okay, and channel that they have is just one, and width and height is 28, okay, and this is the label. Yeah, but now, yeah, this is an image. So the idea of the patching is like previously you have the bad side, channel, and width and height, right? You have to reshape this one to be some value first, okay, to be something that a match with the path, okay. So let's say you can set a patch. Let's say you set 7. So it means that you just try to patch them with each pixel, each 7 pixel, okay, divided. So it means that you have to um set a hash, okay, divided by with the patch size that you want. So it means that you're gonna get 28 by 7. So you're gonna get each sub image as a 4 instance. Okay, so we come up with this final equation. So this is the original one. So you just try to multiply a patch. Okay, and then for each width and height, you just yeah, initially just divide it by the patch that you want. So this is a final one, but maybe we can try to code together. Let's say this is the original, but I think my batch size is 46. Okay, so I set the patch to it first. Okay, maybe I'll put this one later. And then yeah, this is the input shape that I want. Okay, not I want. This is the input shape that I have. Okay, so yeah, we just try to find a patch. You just put the height divided by patch and width divided by patch. So you get a patch already. And then you try to find the input, okay, that you try to multiply height and each patch together. So this is the final. Okay, so now you grouping and reshape them from the original one is 128 to N1 28 28. So yeah, I keep in but the 2 dimension we have to change is yeah, multiply patch together and set a new input them. So now you have the image that was changed already to be this one, 46, 79, and 16. And now, yeah, because you put this one to change the image already, you have to mapping them with the linear. Okay, so we just put the hidden input them again. So I put 16 over here. And yeah, I set this one a hidden dim, just 8. Okay, just set a small one. So now we just mapping with them like from the patching model to the token. Okay, so now we have this one as a token already. But yeah, next thing that you have to do, you have to add the classification token in front of each sequence length. Okay, so you can see that this one it give 49 sequence lengths, but yeah, you have to add one more. So the simple idea is you just call the parameter and set some random, but shape have to matching together. Okay, because this is 49 8. Okay, you have to add 1 8, and yeah, you have to stack for each pad. Okay, and let me stack back. So it means that final value that you're gonna get is pad size and 15 and 8 from hidden dim. Okay. Yeah, and another one that we have is the positional embedding. We just have to have the equation that said each ing is gonna swap and select what is the sine or cosine. Yeah, I just try to show the example from the image result also for the positional embedding, but it will come up again. Yeah, and next, okay. So now you have to create a transformer model. So the things that you have to have is layer norm, first one, and second one is multi-layer perceptron. No, multi-head cell attention. Okay, and the last one is the residual connection. Okay, and this one is, yeah, this is idea of the less that, but yeah, even transformer is they gonna still use it as well. Yeah, and multi-head cell attention. This is the same thing as a transformer that they have. They does not change anything. They just have the sequence and do just mapping with the QKV and do the softmax and multiplication for the cell attention inside. Okay, it's all the same. We just have to think a new thing. Okay, this is almost the same, but the things that we have to think is how does we do the combination of them. Okay, so we look at this model again. This is the entire of the model. So first, yeah, we have input we have input number of patch and head, okay, that you want to set. And yeah, after you have all of them, you have to mapping them, add to the classification token. And yeah, inside the model transformer, you have to have a layer norm twice and one multi-head, okay. And yeah, this is the encoder. You have to have encoder multi-layer perceptron to do a linear LLU. And last one is the final output is a head, okay. We just set the output dim, how many output that task have, okay. So yeah, this is the same as I explained on the board earlier, like you reshape, you set to the mapping layer, you stack, and then you have to add with the positional embedding, and then yeah, you just put the tokens that you get from the image to the layer norm, put to the multi cell attention, okay. But you can see that, let's say this is the output from the multi-head cell attention, right? But you just, if you want to do about the residual connection, okay, you just add token again. That's come from the previous one. It's like you want to use information from the previous one and the one that come from the multi cell attention already to group together, okay, and then get output, and then yeah, put another one for the layer norm again and multi NLP and residual connection again. So then you're gonna get at the final output, but the final output that you have to get it is only one, not only one, but the first one. Okay, that is the token from the classification. So then you just map them and check what is the task task label that you get from output. Okay. So yeah, I have the model already. I just call them and add the input the input shape, set patch again, set hidden dim. Yeah, even it's quite small, but it's okay. And heads is only 2. Okay. And next, I'll put dim. Yeah, tens because it's the image. You just have only tens. Okay. And yeah, the training with the way that I train is almost the same as the earlier class that we have. We have a 10 function. Yeah, they check X and Y, put to the model and check the loss. Okay. This is a classification, right? So yeah, loss that we add is a cross entropy. Okay. Equal times. Yeah, and yeah, I just wanna try to plot the result as well. You can see that each time that I have, okay. Yeah, even first round, the training just gives 70%, but after the train only 5th epoch, okay, they give 91%. Yeah, it's quite impressive. Even they have quite small head and hidden dim, but it can give much good. Okay, so yeah, I check the loss and the epoch that I train as well. So you can see that I think this one is quite straight line, but in actually they do a convert somewhere else. Yeah, but if we get a more higher hit or even hidden dim, I think it's gonna keep a smooth graph as well. Yeah, and last one, I just check the test data set. Okay, with the one that data has not seen before. So yeah, you can see that you can keep 90% of 100 accuracy to checking the image from the emits.